Okay, so now let's do the inductive part, or start the inductive part here. Now, in this part it says each matrix is row equivalent to, or excuse me, here, I'm sorry. So the induction step here, it says assume for n greater than 1 and all m row matrices having fewer than n columns have a unique reduced echelon form. Okay, so that's what we're going to assume. Okay, by hypothesis. Now consider an m by n matrix A, and suppose B and C are two different reduced echelon matrices derived from A. Okay, so what we're going to do is we're going to use the induction to prove that B and C must be equal. Okay, and so in order to do that, we're going to start with another matrix, and we're going to say, hey, let A hat be the matrix consisting of the first n minus 1 columns of A. Okay? So now, what we know is all of the elementary row operations that will reduce A hat, or excuse me, that will reduce A to reduced echelon form will also bring A hat to reduced echelon form. Now, by the induction hypothesis, right, this reduced echelon form for A hat is unique, right? Because we already proved by the hypothesis, because A hat has fewer than n columns, and so we're assuming through the induction step, it says assume that n greater than 1 and all m row matrices having fewer than n columns have a unique reduced echelon form. Okay, since A hat falls in that category, we know that it has a unique matrix that is in reduced echelon form. Okay, so now if there's going to be a difference, it has to be in that last row, or excuse me, in the last column n. Okay, so we're going to finish the inductive step and the argument by showing that the two cannot differ only in that column. So we're going to consider a homogeneous system, and we're going to show this in the next video. Okay? See you then.